All right, Mr. Petit, can you take over from here with the waiting room? All right. All right, so hope y'all are having a wonderful day. All right, so we're gonna go ahead and get going. We're covering all 9 chapters, but it is very basic. So not a lot of different problems with, with the same concept. Just kind of want to hit on a couple of things because we will be here all day. All right, so just want to just make sure kind of touch on some of the main objectives, things that you want to make sure that you know how to do, and get yourself prepared for next week. All right, so we have a math class is made up of 16 men and 18 women. What percentage of the class is female? All right, so we have 34 in the class. That's the 16 plus 18 gives us 34 students total. And so if we have 18 of them that are women, then the percent that are women, plug that in our calculator, 18 divided by 34, and we get 0.529 approximately. So we're going to go ahead and convert that to a percent, rounded 1 decimal place, and that'll be 52.9%. Now, let's say it asks you, because let's take this a little further, because I know sometimes it'll say around the percent 2 decimal places. And that's when you want to be very careful. If you have that box with the percent sign and it says round 2 decimals, then it wants you to round the percent 2 decimals. So you want to be mindful of that and convert to a percent, so that becomes 52. And if I'm rounding it 2 decimal places, 0.94. Now, if it just says round 2 decimals, and there is no percent sign there, and you just see a box, and it's round 2 decimals, then that's 0.53, taking the 2 up because of the 9. Okay. Science class has 42 students. 44% are men. How many men are in the class? Okay, so now I have 42 students total, and a portion of them are men. And we want to know how many men. Okay, so if I have 42 students and 44% of the 42 students are men, think of it that way. Of in math means to multiply. So 42 times 0.44, we want to convert that 44% to a decimal and head to our calculator. And that tells me is 18.48 are men. You cannot have 0.48 of a man. So we would just round that to the nearest whole number and say about 18 men are in the class. Okay. So this is all from module 1. All right, continuing on with module 1, section 1.4. If you want to go back and review this section, we have to determine whether we have observational or controlled experiments. Okay, so remember, an observational study, if you see that it's not randomly selected, you know it's an observational study. Observational studies just compare 2 groups. There is no experimentation, there is no placebo, there is no randomization, there is no assignment to a controlled and a treatment group. It's just simply comparing 2 groups. Okay, so a literacy group wants to determine whether high school students that participated in a recent national reading program had higher standardized test scores than high school students that did not participate in the program. Is this observational or controlled? Well, the first thing that I notice is that I don't see any type of randomization. That's key. So if I don't see a random selection to the 2 groups, then I know it's observation. You are simply comparing the groups. Part B, a study was done to answer the question, what is the effect of different durations of light and dark on the growth of radish seedlings? 3 similar growth chambers, plastic bags, were created in which 30 seeds randomly chosen from the package. So that's a key statement. Were placed in each chamber. 1 chamber was randomly selected and placed in 24 hours of light, another for 12 light and 12 of darkness, and a third for 24 hours of darkness. After 3 days, researchers measured and recorded the lengths of the radish seedlings for the germinating seeds. So as you can see, we're being randomly placed into treatment and control groups. This would be a controlled experiment. The ages of Steve Harvey's kids are given. Steve Harvey has 2 sets of twins, and between him and his wife, they have some kids that are the same age. So just in case you were wondering why so many of the same age. All right, so and this is chapter 3. When we are given this set of data, what's an appropriate graph for this data? Well, for one, the data is numerical. So because it's numerical, we can create a dot plot, a stem plot, or a histogram. Remember that bar graphs and pie charts are for categorical variables only. Okay, so we're going to take this information and we are going to open it in StatCrunch. All right, so we're going to see if we can split the screen here. You can see everything at the same time. I'm sure you guys can see. Can you see both? The PowerPoint as well as StatCrunch?
Well, it's only the PowerPoint.
Okay. All right, let's try this.
Yes.
All right, so we have both. Thank you.
Mm.
Okay, so once we have that data, see, I have the data here under Steve Harvey's kids and their ages. So let's create a, let's just do a histogram. Okay, so to create the histogram, graph, histogram, you can see you have your stem and leaf there, your box plot, and then your dot plot, the other numerical graphs for numerical variables. So either one would work. So you'd select the data and we can go ahead and compute and it will give us a histogram. Okay, the bin widths here, we can see what we're counting by. It's not 5 because you have 2 bins that can fit in that area. So our bin widths are 2.5. We're counting by 2.5. And if you need to change that, you can do so under options. All right, refer back to your videos for detail. Okay, so now that we have the graph, we can see the shape of the graph. We can see our spread, etc., possible outliers, but we're going to go ahead and do some calculations for that. All right, so it says calculate the mean, standard deviation, median, and IQR. Okay, so this is where we go stat, and we want to go to summary stats. Our data is in a column, so select the column where your data is located and compute. And this will give us all of our summary statistics. You see your mean is 32.67. We have our median at 31. Okay, so let's just sit and talk about that for a bit. Let's remember a couple of things about the mean and the median. If these two values are the same, then your distribution is symmetric. And we'll say practically the same as well. They're pretty close. Then we're going with symmetric. However, if your mean is greater than your median, then your data is right skewed. So anytime you have a difficult time seeing the graph, well, you can see the graph, but seeing the shape of the graph, then this is what you can do. Just make these comparisons. All right. And if that mean is less than that median, your distribution will be left skewed. Okay. All right. So a couple of things. We were asked for mean, median, standard deviation. It's going to be the 6.4. Now, this is just a sample. This is not a sampling distribution. We just created a sample distribution or a distribution of a sample. So therefore, we want to go with sample standard deviation. This is not standard error, okay? This is back in unit 1. We didn't learn about standard error until unit 3 with sampling distributions. All right, now the next thing is, do we have any possible outliers? Okay, so for outliers, remember we use the 1.5 IQR rule. And that rule says you're going to take your first quartile, subtract 1.5 IQRs, and any number that is smaller than this number is a possible outlier. Then we're going to take Q3 and add 1.5 IQRs. And any number that's greater than, I can just type, is a possible outlier. Right, so given that information, do we have any possible outlier in this group? So do we have any kids that are extremely old or extremely young from Steve Harvey? Okay, so our Q3 is 38. Well, let's calculate the IQR. Not sure why I started with Q3. All right, Q3 minus Q1. All right, 38 minus 26. So my IQR is 12. Remember, your IQR is the middle 50% of your data. Okay. And it's the best measure of spread for skewed distributions. So we add 1.5 IQRs, and then we take Q1 and we subtract 1.5 IQRs. Oops, 12. All right, so 1.5 times 12, that'll be 18. And 26 minus 18 will be 8. And then 38 plus 18 is 56. So any kids younger than 8 or older than 56 would be possible outliers. All right, so let's go and take a look at the data. And I'm pretty sure Steve Harvey didn't have any kids that were that old or young. All right, I'm gonna have to reset. My screen is frozen, so give me a second. Okay. All right, so there's our data, and we can see that, as I stated, there are no kids that are less than 8 years old or greater than 56 years old. All right, so what is the best measure of spread for our data? All right, so based on our shape, let's take a look at that again. Let's go back over to StatCrunch. So let's make sure that I'm sharing the right screen. All right, so we can see when we're looking at our shape, is our shape right skewed? If it's right skewed, that means he has more kids of higher, older ages. Left skewed would say, I'm sorry, I didn't say that correctly. Right skewed would be, if you're right skewed, that means most of your data is on the left-hand side. So therefore, he has a lot of younger kids. If it's left skewed, then that means most of your data is on the right-hand side and your tail is on the left. So that means most of your kids are older. All right, so based on what we can see here, again, you can change your bin width. You can also take a look at that mean and median to just, if you're unsure if this is right skewed, left skewed, symmetric, then we take a look at those numbers and we can determine the best shape of our data. Our mean is greater than our median, so we're going to go with this is a right skewed distribution. Okay. All righty. So that gives us a good recap of SOX, shape, outlier, center, and spread. So now we want to go to the empirical rule. Recall that the empirical rule only applies if our data is symmetric and unimodal. In other words, it only has one mound and my left side, right side are roughly the same. Okay, so if this is the case, remember that the center of this distribution is based on a sample, would be X bar, and the standard deviation would be S, sample standard deviation. So it tells us we have a mean of 143 with a standard deviation of 29. So because it's symmetric, remember that the mean is in the center of our distribution. So we want to know approximately 68% of women weigh between what two values? So the empirical rule tells us that 68% of data lies within one standard deviation away from the mean. 95% lies within two standard deviations, and almost all of the data, or 99.7% approximately, within three standard deviations of our mean. So standard deviation is the distance away from the mean. So being that my standard deviation is 29, if I go 29 to the left and to the right of 143, then that will tell me where 68% of my data lies, because that would represent one standard deviation away from my mean. Okay, so 143 minus 29, that would be 114, and 143 plus 29 would be 172. So about 68% of all women weigh between 114, of the sample weigh between 114 and 172. Okay. All right, what percent of women weigh between 56 and 230? Okay. So then we would have to keep going. So how many standard deviations away from, question mark, how far are we going? That's going to get us to 56 and 230. Okay. So in this case, if you take the 143, we know it's not one standard deviation because this is this one. 68% is one standard deviation away from our mean. Okay, so how many standard deviations is 56? So if I subtract, let's say 2 times 29, well, 2 times 29 would be 58. And 143 minus 58 is not 56. So let's try 143 minus 3. Is it 3 standard deviations? So 3 times 29, that's 87. And 143 minus 87 is 56. So we can do the same thing to the right-hand side. If we try 143 plus 3 standard deviations, that's 143 plus 87, which is 230. So 56 and 230 are 3 standard deviations away from our mean. Therefore, 3 standard deviations away from the mean represents 99.7% of our data. All right, so now let's calculate the Z-score of a woman who weighs 187 pounds. Now, the Z-score would represent these numbers. It tells you how many standard deviations away from the mean a data value will lie. Okay, so to calculate your Z-score, you're going to take the data value you're trying to convert, subtract the mean, and then divide by the standard deviation. So I'm converting 187. A Z-score is a standardized score, so it doesn't have any units like the 187 is in pounds. Okay, so the 143 is the mean divided by 29. Okay, so we use our calculator and we're going to take the numerator and divide by our denominator. And that gives us 1.52 approximately. So that says that this woman in particular weighs 1.52 standard deviations above the mean, which would be your average. Here we want to look at, and this starts unit 2. We're looking at a correlation between ice cream sales and temperature. Is there a correlation between how much ice cream we sell and the temperature in degrees Celsius? Okay, so we're going to take that data. Remember on the test, you can just simply click on the little icon to open the data into StatCrunch. You do not have to manually enter it unless you have some issues with the two systems while you're testing, but always remember you can contact the HonorLock agent and they'll be happy to assist you in getting StatCrunch to work for you. All right, so I have the data here, temperature and sales. Now, temperature would be our X, our explanatory variable, our independent variable. Sales will be the Y, that's your dependent variable, because in this case, we're trying to see if the temperature drives the sales. In other words, if it's cold, would I tend to have fewer sales? Or if it's hot, does that give me a correlation with more sales? We wouldn't use sales as the X and temperature as a Y, because your sales, it's not going to drive the temperature. Temperature is the independent variable. Okay, so that's how we know which one to enter as X and which one to enter as Y. You just ask yourself, well, which one can possibly influence the other? Okay, so in this case, we would like to create the scatter plot. So graph, scatter plot, choose your X and your Y, and compute. We need to see the scatter plot. You need to see any graph before you try to summarize your data. Before you try to see the best measure of center and spread, mean, median, IQR, standard deviation, I need to know if my data is symmetric or it's skewed. If I have two numerical variables and I'm creating this scatter plot, I need to know that my data is linear. Because if my data is not linear, then none of the following applies. We want to determine if there's a correlation between these two variables and how strong that correlation is. Well, it has to be linear. So now that I can see that my data does follow a line, now I can calculate my regression. So we're going to go stat, regression, simple linear, select your variables, compute. Okay, so you are given your regression equation, it's not allowing me to highlight it. All right. So here's your regression equation. And from that equation, we have a couple of variables of interest. That is your standard form of the equation. We have y hat. Y hat is our predicted value of y. We use the regression equation to predict values of y. We have A, that's our y-intercept. That is when the graph crosses the y-axis, and that is always when x is equal to 0. And then we have our slope. That tells us if we have a positive or a negative association, how is y changing based upon each value of x, an increase of x. All right, so next we have our correlation coefficient. This is our R, symbol R. And we also have our coefficient of determination, which is R squared. Okay, so R is what we use to determine our strength. Once again, it is only useful if my association is linear. R lies between 1 and -1. The closer it is to +1 makes it a strong positive. Closer it is to -1 makes it a strong negative. The closer it is to 0 makes it weak. Okay, if it is equal to 0, there's no correlation at all. So we can see we have a 0.988. That is a very strong positive linear association between ice cream sales and temperature. So let's see if I can split the screen again. All right, so the problem says that we've calculated our regression, we've interpreted our correlation, we've said it was a strong positive, and now we want to calculate, and we've already calculated our correlation of coefficient, that's the R squared, 0.976, but we need to interpret it. Okay. So in our interpretation, let's clear out drawings. So for your interpretation for the coefficient of determination, it is the percent of variation in y that can be explained by x. So in other words, it was 97.6%. So 97.6% of the variation, which are differences in our y variable, which will be our ice cream sales, can be explained by x, which was our temperature. So that accounts for a lot of the changes in your prices. Temperature does. A couple other things that I don't have listed here, but things that we definitely want to make sure we know how to do. Let's go back. We need to know how to interpret our slope as well as our y-intercept. So let's go back and get that formula, the regression. All right, so let's take that equation and interpret. So here's my slope. So to interpret slope, and I want to make sure that you all are seeing what I'm seeing. Okay, things we're good to go. All right, so to interpret your slope, we would say as x increases by 1 unit, this is your general interpretation, y is predicted to increase or decrease by the amount of the slope. So in this case, as X is temperature, increases by 1 unit. The unit of measure in this problem was degrees Celsius. So we would say for each additional 1 degree Celsius, then it says Y is predicted. Y is sales. So ice cream sales are predicted to increase or decrease. This is based on the slope amount. The slope is positive, so it's going to be increase on average by the amount of the slope, which is 32.54. And now we got to get the units of measure correct. Since we're talking about Y is increasing by this amount and Y is sales, and that means there should be a dollar sign. Okay. So for each additional 1 degree in Celsius, our ice cream sales are predicted to increase on average by about $33. Okay. All right, the next thing, be able to interpret the y-intercept. Remember, the y-intercept is when x is equal to 0. So therefore, your interpretation, x is temperature. So at 0 degrees Celsius, okay, so if temperature is 0, your y-intercept is negative 2.05.84. So that will be your sales. Sales will be equal to that value, predicted to be that value. So at 0 degrees Celsius, sales predicted to be negative 205.84. All right, and then you would say this value is meaningless because we cannot have a negative value for sales. All righty. All right, so that takes us through regression. So now we would like to look into probabilities. So chapter 5, this kind of covers some of the two-way tables from chapter 1 as well. I figured we'd do it all in chapter 5, right? So given this two-way table, remember a two-way table or a contingency table allows you to compare 2 categorical variables. So in this case, we're looking at the flavors of ice cream versus 2 sports, soccer and football, right? So if one person was randomly selected, what's the probability that person would like vanilla? All right, well, we have 50 people that like vanilla, and there are 72 total in the study. Okay. Well, what if they like vanilla and football? So here we want to look for an intersection. Right, so I like football and I like vanilla. So I have 32 people that like both out of 72. Now, vanilla or football. Okay, so this is where you want to look at your formula sheet. So the probability of A or B would be, you'd add the 2 probabilities and you subtract out the probability of A and B. So in this case, let's let A be vanilla and B is football. So the probability that I like vanilla, we calculated that earlier as 50 over 72. Probability I like football, well, there are 42 people total that like football. And then you subtract out the probability that I like both, right? So that's the vanilla and football. So that's the 32 out of the 72. Okay, so if you're to add these together, 50 plus 42, that's 92. Subtract 32, we have 60 out of 72. Now, what's the probability? I like soccer, given I like chocolate. So if it's given that I like chocolate, I'm only interested in those who like chocolate. And we have 22 that like chocolate. So that becomes my denominator. And out of the 22 people that like chocolate, there are 12 of them that like soccer. Okay. So let's flip it. The probability I like chocolate given I like soccer. Now, in this case, I'm interested, my condition is that I like soccer. Well, there are 30 people who like soccer. And out of those 30 people, these are the only people we're interested in. 12 of them like chocolate. Okay, so those are called conditionals. Also in chapter 5, we had repeated measurement probabilities. So this is if I'm taking more than one. I'm randomly selecting more than one. So according to a recent study, 59% of households from a certain large region no longer have a landline and instead only have cell phone service. Suppose 5 households from the region are selected at random. So we have 5 selections. And let me add in here that we are assuming independence. All right, so that piece is key for me because on your formula sheet, you should have that if events are independent, then the probability of A and B is the same as the probability of A times the probability of B. It's only if they're independent, we can use that multiplication rule. So if I have 5 people, what's the probability all 5 of them only have cell phone service if we know that 59% of households, have cell phone service? Okay, so in this case, so the probability, all 5, well, the probability of each person is 59%. So being that they're independent, I can multiply the probabilities of each person. And being that I have 5 of them, that is equivalent to just saying, take 59% and raise it to the 5th power. Okay. So do that calculation. That's approximately 0.07 or 7% approximately. Okay. What's the probability none of the 5 have only cell phone service? Okay, so if the chances that I have cell phone service only is 59%, the chance that I do not is the complement. So again, on your formula sheet, you have a formula for complements. And that formula says, let's see, the complement of event A is 1 minus the probability of event A. All right, that's as a decimal. You can convert 1 to a percent, 100%, being that our value is in percent. So we have 100% minus 59% is 41%. All right, let's go ahead and make that a decimal, 0.41. So there's a 41% chance that I do not only have a cell phone service in my home. All right, so now the probability that none of the 5 have only cell phone service, if the probability of having only not having cell phone service, only cell phone service is 41%, and I have 5 people, I'm going to raise that to the 5th power. All right, so that gives me 0.01 approximately. Well, what's probability at least one of the 5 only have cell phone service? The probability of at least one is a complement to none. So I'm using the complement formula, which says to subtract it from 1. We just calculated the probability of none of the 5 having cell phone service to be 1%. So that means the probability of at least one person out of the 5 having only cell phone service is about 99%. So again, the independence formula has to come into play when you're working out repeated measurement problems. Okay, because you just simply multiply their probabilities. Don't multiply by how many people you have, you multiply their probabilities. Right? All right, chapter 6. Now, this is when we talked about continuous random variables. Continuous random variables are not countable. You cannot count them on your fingers. Okay, discrete random variables from chapter 5 are countable. Okay, so we want to assume the lengths of pregnancy for humans are approximately normally distributed with a mean of 267 and standard deviation of 10. Okay, now in this case, I'm referring to the population distribution because it says the lengths of pregnancy for humans. It didn't give me a sample. It's not talking about a sampling distribution. So it's talking about all humans. So it's referring to the population distribution. So the mean of a population distribution is mu, and the standard deviation is sigma. Okay. So what is the probability that a randomly selected human is pregnant longer than 270 days? So we're looking for the probability that mu is greater than 270. So being that our distribution is normally distributed, the center of that distribution is at 267 with a standard deviation of 10. So, just keep adding and subtracting 10. And we want 270 and greater than. Okay. All right, so what percent is that? So this is where we go over to StatCrunch. All right, so let's read. All right, so to calculate our probabilities, stat calculators. The distribution is normal. We have our mean mu of 267 with our standard deviation of 10. And we want longer than 270 days. Compute. Okay. So about 38%. And if you're asked to round the percent 2 decimals, 38.21% in this case. So then it says, well, what pregnancy length is at the 15th percentile? Okay, so now this is where we have to go back and understand percentiles. Percentiles always read to the left. So that means we have 15% shaded from the left. And the question is, what is your data value? What is your X based on a 15th percentile? So being that I've given you the probability in this case as 15%. So if you plug in 15% where probability would go, and then you need to change your sign because it's a percentile. So we've shaded to the left, which means less than, and that will give you your data value. Anyone in the 15th percentile, that's anyone that has been pregnant 257 days or less. Okay. All right, next question. Standard normal distributions. So a standard normal distribution, we're not interested in the X values. We are interested in the Z scores. Okay. Anytime you see standard normal, that means your distribution has a mean of 0 and a standard deviation of 1. because these will be our z-score values. So we are interested in the probability that a z-score is greater than 1.21. So whenever you're dealing with a standard normal distribution, come over here, and again, my mean is 0 and my standard deviation is 1. That will convert your X values to z-scores. Now, it's not going to change what you see here in StatCrunch, but because you plugged in that 0 and 1, StatCrunch knows that we're using z-scores. All right, so we want a z-score greater than 1.21 and compute. And there's your probability. Okay. So what about a z-score between these two numbers? So we would press between. Again, mean is 0 and standard deviation is 1. We just enter those two numbers and compute.
Can you show your screen using StatCrunch doing that?
Sorry. Okay, so you guys don't see the screen.
Thank you.
Okay. All right, so I've been here for a while, so you guys haven't been seeing StatCrunch for the past two problems?
I just didn't see it for that problem.
Oh, that's interesting. Okay, let's. All right, so let me do that again. All right, thanks for letting me know. All right, so we press the between button, mean of 0, standard deviation of 1, and then you just enter the two between values. For the first one, that would be under standard because we don't have between two numbers, and then greater than the 1.21. So anytime you're dealing with probabilities of a distribution, you're going to come to the same place, regardless whether it's a population distribution or a sampling distribution. All right, so that should take us into chapter 7. Screen again. All right, so in chapter 7, we want to know and make sure we have a good understanding of the differences between our parameters and statistics, populations and samples. So remember that a population is everyone that you're interested in studying. A sample is a small portion of that population, a subset of the population. A parameter is a numerical value of the population. And a statistic is a numerical value of the sample. Okay, so just remember that the first letters start. So you know parameters should go with populations because they both begin with the P, and statistics go with samples because they both begin with an S. So all daily maximum temperatures in August last year for all major US cities were recorded. So all of the daily temperatures in August, that would represent my population. I'm sorry, that would represent the parameter, okay, because that's a numerical value of the population. Okay. All right, so the mean of all, I said it right the first time, I apologize. The mean of all of the maximum temperatures is going to be the parameter because it's the numerical value of the population. All of the temperatures in themselves would be my population. Okay. Okay. Now, if I said, let's take 10 instead of all, then that will be a sample. And then if I say now calculate the mean of the 10, that will be a statistic. Okay. Sampling distributions. A sampling distribution says you take many samples of the same sample size from the same population. Create a histogram. And as long as certain conditions have been made, that distribution should be normal. Whenever you're dealing with the sampling distribution, it is a distribution of statistics. So it's a distribution of your X bar, your sample mean, or your P hat, your population proportion. So anytime you're being asked to calculate, for example, the probability of an average, you know you're converting to a sampling distribution. When you convert to a sampling distribution, now in chapter 7, we dealt with proportions. So the mean for proportions would be P. And then your standard deviation converts to standard error when you're dealing with sampling distributions. And let's write that formula in. Okay. All right, so, in 2018, it was estimated that approximately 45% of the American population, so 45% of all Americans, that's P, population proportion, watches the Super Bowl yearly. Suppose a sample of 150 Americans, that's my sample size, N, is randomly selected. Random is key. After verifying the conditions of the central limit theorem are met, find the probability that more than 48% of Americans watched the Super Bowl. Okay. So in this case, checking the central limit theorem, the first condition is that we have a random selection. The second condition is that you have to have at least 10 successes and 10 failures. So 10 people to say they watched it, 10 people to say they didn't. So since I have 150 Americans and 45% watched, then 150 times 45% is greater than 10. So that would be the number of successes. The number of people that would not watch, well, we would have 55% of the population that does not watch. And if you multiply that by 150, that's greater than 10 as well. So I have enough successes and failures. The third condition says I have to have a large enough population. We're talking about Americans. So yes, population size, that condition has been met as well. So since all conditions have been met, we want to find the probability and I should have the wording on this is not good. I needed to update that. All right, it should be that your sample more than from your sample proportion. You're calculating the probability that your P hat is greater than 48%, not out of the population. So let me correct that question. The wording on that question, we're finding the probability that more than 40% of our sample. Okay, so that's what we're missing. More than 40% of our sample, not of all Americans. All right, so in this case, because I'm finding the probability of my P hat, a sample proportion, that lets me know I'm in a sampling distribution. As long as those conditions have been met, my mean is P, my standard deviation converts to standard error. I've given you the formulas. And the last thing is your sampling distribution is normal. As long as those conditions are met, those are the three conclusions you can draw. So because my sampling distribution is normal, I can now calculate the probability using a normal CDF, or the normal function that we had in our stat crunch. All right, so I'm going to try to split the screen again. So guys, let me know, please, if it's not showing. All right, are we seeing both? Are we seeing stat crunch as well as the problem? Okay, I see the answers in chat. All right, thank you. All right, so remember that you're in a sampling distribution now. So your mean is going to be your P. Okay, so your P was a 45%. Remember I said that this should be of the sample. All right, so because it's based on the sample, this is my P hat value, sample proportion. Okay, so to calculate standard error, if we know P, we use P. If we don't know P, then we can use P hat because it's the estimator for P. Remember, statistics estimate parameters. So my P is 45%, and 1 minus 45% is 55%. And my sample size, we had 150 Americans. So go to my calculator and enter that information in. That gives me approximately, I'll say 0.0406. Okay. So again, remember your mean is your P. So I'm substituting 0.45 for 45%. Standard deviation is my standard error, 0.0406. Try not to round that too much. Like I wouldn't round it to 2 decimals, even if the test says round 2 decimals. Or if it says, hey, what's your standard error, round 2 decimals, you can put 0.04 in. But then if the next question comes back and says, what's your probability, I wouldn't use the 0.04 because that might end up giving you a rounding error. And being that you don't have access to your final exam after you take it, then you don't know if you had some rounding error issues and what your professor would do about that. So therefore, try to take that value out maybe 4 or 5 places just to make sure that you don't run into those issues is my recommendation. All right, so then the problem says find the probability that more than 48%. So 0.48 and compute. Okay. All right. So our next problem says, well, what happened with people in Alaska? Drivers in Alaska drive fewer miles yearly than motorists in any other state. The annual number of miles driven per licensed driver in Alaska is 9,170. Okay, so this is a means problem. Proportion problems are yes or no. It's a value of, a percent, a number out of another number. A means problem says that the survey question has to provide a numerical value. So since I'm telling you how many miles have been driven by Alaskans, then this is a means question, not a proportions question. Okay, so since that's based on the population, that's my population mean mu. Assume the standard deviation is 3,900. That will be population standard deviation sigma. We have a random sample of 100. That's my sample size. And it says the mean number of miles driven yearly for the sample is calculated. So that sample mean. After verifying the conditions of the central limit theorem, find the probability that the mean number of miles driven is less than 8,000. So it's telling you right here, mean number of miles driven yearly for the sample is calculated. It's telling you, remember, a sampling distribution is a distribution of a statistic. And since we are calculating X bar, then this lets me know I'm in a sampling distribution here. We're talking about calculating probabilities of sampling distributions. So what are the conditions for means? Central limit theorem for means says we have to have a random selection. We don't have successes and failures in means because you don't have yes or no type questions. You have numerical values. So the second condition that checks to determine if you have a large enough sample size would be, is your population distribution normal? This problem doesn't give us that information. The second would be if you don't know anything about the population distribution, or if it's not normal, do you have at least 25 in your sample size? And we do, we have 100. So the second condition has been met. Third condition is still the same. Our test for independence, large population test, we're talking about Alaskans, plenty of Alaskans, so it just needs to be 10 times larger than your sample, and we definitely have more than 1,000 Alaskans. Okay, so all conditions have been met. Now, what does that mean? That means my sampling distribution is approximately normal. That means my mean is the same as mu. That's mu of X bar. The average of all of my statistics should be the same as my population mean. And it also, my standard deviation converts to standard error, and that will be sigma divided by the square root of n. All right, so let's go ahead and do that calculation before we plug it in. So sigma is 3,900, n is 100, so that's 3,900 divided by 10, so that's going to be 390, and mu is 9170. And we're looking for the probability that we're driving less than 8,000. That mean 9170 with a standard deviation converted to standard error of 390. We want less than 8,000. And we compute. All right. So very, very small percentage there. It's 0.1%. All right, so that's sampling distribution, calculating probabilities of sampling distributions for proportions as well as means. Okay. So next we'll do confidence intervals for proportions and means. So in this first question, a stat instructor randomly selected 4 bags of oranges, each labeled 10 pounds, weighed the bags. You see the weights listed. So I'm giving you data. So of course, the next thing you're going to do is enter that data into StatCrunch. So make sure you guys are still seeing StatCrunch. Okay, so once it's entered, it says, all right, assume that the distribution of weights is normal. Remember, this is a means problem because we're dealing with numerical values. So remember the conditions say random selection, does say so. Second condition, large enough sample. I only have a sample of 4, but it tells me that my population distribution is normal because it says the distribution of weights. That refers to all weights, that refers to the population. So because that's normal, I can have a small sample size and still be able to calculate a confidence interval. Now, the thing you want to remember is that anytime you're calculating a confidence interval or a hypothesis test for means, they don't follow the normal, they follow the t-distribution. These are the only 2 that you would use a t-distribution for. All right, so we're going to do a 90% confidence interval for mean. So we're going stat, oops, let's try that again. t-stats. One sample, and I gave you data. So say with data. Select your data. Doing a confidence interval, so select confidence interval. The confidence level, it said was 90%, so 0.9. You want to show your critical value, just in case you have to calculate margin of error, and go ahead and compute. All right, so there's your standard error. So whenever you're calculating confidence interval and hypothesis test, you don't need to calculate your standard error using the formula. You can just simply run the test and it'll give you that information. All right, the critical value that you need to use is here. Now, margin of error is always standard error times critical value. So when your test asks you for margin of error, just simply multiply those two numbers. And then here's your confidence interval. It's the lower limit and the upper limit. Remember that a confidence interval gives you plausible values for your parameter. So therefore, we are 90% confident that the mean weight of all bags of oranges is between 9.2 and 9.8 pounds. We're 90% confident that the mean weight of all oranges between 9.2 and 9.8 pounds a bag. So therefore, is it plausible that the mean weight of all bags is 9.5? And you would say yes, because 9.5 lies within this interval. Part B, consider a poll that reported that 525 out of 900 adults from a certain region have tried marijuana. Calculate a 95 confidence interval for the proportion of all adults who have tried marijuana, assuming all conditions have been met. All right. Now, this is a proportions question because I'm telling you a proportion, 525 out of 900. Okay. So you're doing a confidence interval for proportions. So anytime you do that, that will be stat, proportion stats. We only have one sample with summary. You don't have data for this problem. You have data, you can get data for mean questions, but we don't give data for proportion questions. All right, so your number of successes, 525, reported they did out of the 900. Select your confidence interval at 95%, show the critical value again, and compute. Okay. So there's your standard error, sample proportion, if it asks you for that, your critical value. So remember again that we multiply the standard error times the critical value if you want margin of error. And then here's our confidence interval. So in this case, we are 95% confident that the proportion of all Americans who smoke marijuana is between 55 and 62%. So now a follow-up question to that could be, well, can we say that a majority of Americans smoke marijuana? And you would answer, yes, this does satisfy that claim because the entire interval lies above 50%. Right. So we have one last concept, and that's hypothesis testing. Now, if you need very detailed instruction or more examples, let's refer back to the unit reviews that we did, and also make sure that you look at all of the wonderful things we have under modules. If you use your calculator, then take a look at our YouTube channel for the calculator use with Professor Keinert. And then Professor Ross has the the videos that will teach the material as well if you need a little bit more reviewing on that information. All right, so in country A, the population mean height for 3-year-old boys is 37 inches. Suppose a random sample of 35 3-year-old boys from country B showed a sample mean of 37.4 inches. With a standard deviation of 2 inches, assuming the heights are normally distributed, is there evidence the mean height in country B is higher than country A? So in this case, we would like to do a hypothesis test for means. We're talking about means. Remember, we have here a numerical value. Okay. Now, we have a random sample of 35, so my sample size is large enough for the central limit theorem. It says random. We have a bunch of 3-year-old boys, so my population is large enough as well. So all conditions have been met. So my hypothesis would say, well, the information that I was given was that the mean height is 37. And my research hypothesis says, well, is there evidence that it's higher? So greater than 37. Okay. So we have a hypothesis test for means. The same place, remember up here what I told you? Anytime you're dealing with confidence interval or hypothesis test for means, we're using that t-distribution. So once again, we're going to go to the same place we went for confidence intervals, t-stats, one sample. And I didn't give you data this time. So we're going to go with summary. So your sample mean, it says, let's move this over. Sample mean of 37.4. Sample standard deviation given at 2 with a sample size of 35. We want the hypothesis test. We stated our hypotheses. We were told that it was 37, and we believe it is greater than 37. And that is all you need. You do not need to show a critical value because that's for a confidence interval, not a hypothesis test. Go ahead and compute. There's your standard error if you're asked for it. Degrees of freedom, your t-statistic is given, and then your p-value. So what are our rules? The rules say that if my p-value is less than or equal to my alpha, we are rejecting the null hypothesis. And if my p-value is greater than my alpha, we do not reject the null hypothesis. Okay, so then the question is, what is our alpha? Alpha is the level of significance. And if it's not stated, then we use 5%. This p-value is greater than 5%. That means I am not rejecting the null hypothesis. And if I do not reject the null hypothesis, that means I do not have enough evidence to support my alternative hypothesis because I believe I have enough to support the null. So I do not have enough evidence to support the alternative hypothesis. The alternative hypothesis says that country B is higher than country A. So I don't have enough evidence to support that. In other words, my data is statistically insignificant. There is nothing that we see in our study that makes me believe that what I've been told, which as the average height of 3-year-old boys is 37, is not true. So the data was statistically insignificant. You didn't show me anything that I didn't already know or believe. All right, and our final question. Let's clear this out. All right, concern was raised in Australia that the percentage of deaths of Aboriginal prisoners was higher than the percent of deaths of non-Aboriginal prisoners, which is 0.27%. Sample of 6 years of data was collected. found that out of the 14,495 Aboriginal prisoners, 51 died. Do the data provide enough evidence that show that the proportion of deaths is more than 0.27%? All right, so once again, state my hypothesis, assuming all conditions have been met. Now, this is a proportions question. Remember, this was means. Okay, so therefore, my proportion that I was told, 0.27%. So we need to convert that 0.27% to a number. Move your decimal 2 places to the left. Remember, you cannot enter percents into your technology. Okay. The alternative would say P is more than that value. Right? We have our sample size. We have our, and I hate to say it, number of successes. That's the number of people that died, but that would unfortunately be considered our number of successes here. Okay. All right, so since this is a proportions question, we're going back to proportion stats. One sample with summary. Right, enter in the 51 successes out of our sample size. We want a hypothesis test. And we enter in our hypotheses. We want greater than, compute. All right, so our p-value is at 0.03. Again, alpha was not stated, so we're using standard alpha at 5%. Since my p-value is less than my alpha, we are rejecting the null, which says we do have enough evidence to support the alternative, which says that it is greater than for Aboriginal prisoners. Okay. Our data is statistically significant because there is something that happened within my data that made me question my null hypothesis and believe the alternative was true. All right, so I hope that was helpful. Do we have any questions? All right. Well, I wish you all the very best on your final exam. And for the rest of your semester, all of your final exams, just remember that your instructors do not have office hours, regular office hours next week. So please check with them to see the availability that they will have in their office for next week. It will be different. And don't forget, you don't have classes next week outside of your final exam. So check your final exam times. All right. Wish you all the very best. And the recording will be sent out, posted from the Learning Commons. All right, y'all take care.